Myself, Dr. Naresh Kumar, Associate Professor, Department of Mathematics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today, I want to discuss a very important topic, Legendre homogeneous linear differential equations. Legendre is a very famous mathematician who gave a standard form of linear differential equation, and he discussed about the solution of Legendre homogeneous linear differential equation. So here I want to discuss today how we can solve Legendre homogeneous linear differential equation, and I want to define Legendre homogeneous linear differential equation in detail. So Legendre homogeneous linear differential equation. The general equation of Legendre homogeneous linear differential equation is, here I am giving following formula following a general differential equation. That differential equation is known as a Legendre homogeneous differential equation. So now we discuss here an. An is any constant, any number, and in bracket ax plus v. Ax plus v. Ax plus v, this is linear equation. Ax plus v, this is linear equation. Linear equation of one variable of 1 degree. Of 1 degree. This is linear equation of one variable and 1 degree. 1 degree equation. Suppose 2x plus 3, 1 plus x, x minus 1. These are known as a linear equation of one variable of 1 degree. Linear equation of one variable. So here in bracket there is linear equation of one variable of 1 degree. Ax plus b. So the power of linear equation n is equal to the order of derivative. Similarly, next term, this is an minus 1. An minus 1 is constant. And again in bracket is linear equation of one variable. And power is n minus 1. So this power equal to the order of derivative. And here is a1. A1 is number. And in bracket ax plus v. This is the linear equation of one variable. Linear equation of one variable, and with multiply first derivative coefficient. The linear equation of one variable, the power of this bracket is 1. So power of 1 is, so here is derivative of order 1. And in last a naught. A naught is again number, and y is function of x. And derivative is 0 here. Because here ax plus b to the power 0. And in right hand side is some function of x. This is equation 1. This is general Legendre homogeneous linear equation of n order. So this equation is given by the Legendre mathematician, and he gave in detail how we can solve this equation. So now we want to discuss in detail how we can solve this equation today. There in our equation, differentiating with respect to x, d over dx is capital D. Here x is independent variable and y is dependent variable on x. Y is dependent on x means y is some function of x. y is some function of x here. Okay, so this is the main general Legendre homogeneous linear differential equation. Definition of Legendre homogeneous linear differential equation. How we can define the Legendre homogeneous linear differential equation? So the definition is the power of linear equation, any linear equation. Linear equation means 2x plus 3, ax plus v, and 1 plus x, and 1 minus x. These are all linear equations. Okay. General equation is ax plus b. So the power of linear equation of one variable x, say ax plus b of 1 degree, power degree of x is 1, is equal to the order of derivative in each term. This property verify in each term of the given Legendre homogeneous differential equation. And in LHS, left hand side, this property apply in left hand side, and right hand side is some function of x. Okay, so if this property verify in any equation, then that equation is known as a Legendre homogeneous linear differential equation. Again I repeat definition, the power of linear equation. Linear equation means ax plus b, linear equation of one variable of 1 degree. Degree means power of variable. So this is 1 degree linear equation of one variable x, say ax plus v, is equal to the order of the derivative in each term in multiply in left hand side, and RHS is some function of x, say phi x. RHS is some function of x, say phi x. So now again I am writing same equation 1 which is discussed in last, just an ax plus b to the power n. This is the linear equation of n power n degree. Linear equation ax plus v of one variable of power n is multiplied with nth derivative. Next is linear equation of power n minus 1 multiply with n minus 1 derivative, multiply with derivative of order n minus 1. Similarly, in each term, this process verify, this property verify. In last A1 is constant, ax plus v is linear bracket of power 1 multiply with first order derivative, and here A0 is constant, ax plus b to the power 0 here. So the power is 0, so derivative of 0 order here, and in right hand side is some function of x, that is phi x. This equation same as 1. This equation is general Legendre homogeneous equation where A0, A1, where A0, A1, A2, An are constants, and phi x is function of x. X is independent variable in this equation and y is dependent on x. Equation 1 is known as a Legendre homogeneous linear differential equation. We will change equation 1. Here we want to change this equation 1 in linear differential equation of nth order with constant coefficient. Okay, this is homogeneous equation. There is variable in multiply in the derivative. In each derivative there is some derivative, some variable multiply in each derivative in each term. But now we want to this equation 1 in nth order with constant coefficient. Linear differential equation of nth order with constant coefficient. If we change equation 1 in constant coefficient, then we can solve with the help of y is equal to CF plus PI method, which we have discussed in last lecture's detail. So that method we can apply in this equation after changing. So how we can change here? We will discuss here method. We will discuss the method change of variable. Change of variable. if in our equation x variable is given and then we can change a independent variable x to in another independent variable z, t, any other variable we can change. So how to change Legendre homogeneous linear differential equation in linear differential equation with constant coefficient? We want to discuss here in detail how to change the Legendre homogeneous linear differential equation in linear differential equation with constant coefficient. So to change equation 1 in constant coefficient, then we change a independent variable x, we change x to another independent variable z. Means we want to change x to z. X is independent variable. In our question, this independent variable we want to change in another independent variable z. When we convert x to z, then our differential equation, Legendre homogeneous linear differential equation, change in constant coefficient differential equation. Okay? When in place of x in our question, we convert z, then our differential equation change in linear differential equation with constant coefficient. And then we can apply a method y is equal to cf plus pi. So we will discuss here in detail. Following given method is known as a change of variable. Change of given independent variable x to another independent variable z. Change of independent variable means any variable is given in the question. Suppose x is given independent variable in our question, and then we change this independent variable x to in another independent variable z, t, u, v, any other independent variable. Then this method is known as a change of independent variable. This is main method, change of independent variable. Let us consider that following assumptions. We are considering some assumptions here. With the help of these assumptions, we can change our independent variable x in another independent variable z. So here let ax plus v, this is linear equation, ax plus v, जैसे 2x plus 3. Here is ax plus v. Ax plus v equal to let e to the power z. We are considering this function. This result considering here. Ax plus v equal to e to the power z. Suppose in our question is 2x plus 3. 2x plus 3 is equal to e to the power z. Suppose 1 minus x is in our question. 1 minus x is e to the power z. Suppose 1 plus x in our question. This is e to the power z. So in our question given this bracket, then we consider, if this bracket, then we consider this, if this bracket, then we consider this. But in general process, in our equation given ax plus v, so ax plus v consider e to the power z. Then taking log on both sides into this equation 2. This equation 2. In equation 2 taking log on both sides, then we get here. So log ax plus v taking this side, this function taking log ax plus v equal to log e to the power z. Log e to the power z. In equation 2 taking log on both sides. Apply formula log x to the power n. This formula apply log x to the power n. This is log x, n log x, n log x. N comes before log. N comes before log here. So formula is n log x. X log x to the power n, convert in n log x. So we apply this formula in this equation. Here is log e to the power z. Z comes before log. So z log e. Z log e. Apply formula here. Log e is 1. Log e is equal to 1. So our question log ax plus v equal to z. Or z equal to log ax plus v. This equation 3. We get here z equal to log ax plus v. Be considering ax plus v equal to e to the power z. Ax plus v equal to e to the power z. Then we find the value of z equal to log ax plus v. Means here ax plus v equal to e to the power z. Then we find then z equal to log ax plus v. Okay, this result we find. If this result we considering, then this result we find here. Okay, ax plus v is equal to e to the power z. Let's say e to the power z. Then z equal to log ax plus v. How we can find this? This is a process. So now this equation 3. Z equal to log ax plus v, equation 3. Differentiating with respect to x to equation 3. Then we get. So differentiating with respect to x here, dz upon dx. Differentiating z with respect to x. This is left side. Right side is log ax plus v. So differential of log x is 1 upon x. Differential d over dx of log x. So this is 1 upon x. We apply this formula here. So differentiation of log ax plus v, 1 upon ax plus v, and ax plus v, differentiation of ax plus v into a x1 b0. So differentiation of this a. So differential this a upon ax plus v, where d is dy dx, differentiating with respect to x, and d dash is differentiating with respect to z. D dash means z or dx means d. D is differentiating with respect to x, and here d dash means differentiating with respect to z. This is equation 4. dz over dx equal to we get a upon ax plus v. Okay, so capital D is known as a d over dx, and capital D dash is known as a d over dz. This equation is 4. Now 1 point. We have considered here 1 point. 1 point is changing dy dx in dy dz. First of all, we change in dy dx in dy dz. How we can change here? Then dy dx means differential of y with respect to x. This equal to dy dx multiply dz and divide by dz. In dy dx multiply dz and divide by dz. Okay, so now denominator dz and dx interchange. This interchange to this interchange to this. Then we get dy over dz and dz over dx. Okay, this is equation 5. Now from equation 4, dz over dx is a upon ax plus b. So from equation 4, value of dz over dx. What is dz over dx is a upon ax plus b. Ax upon ax plus b, putting in 5. Then we get y equation 5. What we get here? dy dx here. dy dz this in 5. dy dx into a upon ax plus b. This is equation 6 here. Here we have changed dy dx in dy dz. Why above method? Change of variable. So here we have changed dy dx. dy dx have changed in dy dz. X variable convert in variable z. By above method. Above method means change of independent variable. So now here, this ax plus b multiply to this side. In this equation 6, multiply by ax plus b on both sides. Then this ax plus b cancelled. Then we get here ax plus v dy dx equal to a dy dz. This equation 7. At last we have, what we have? Ax plus v dy dx equal to a dy dz. But dy dx, what is dy dx? dy dx we write dy. What is dy dz? dy dz we write d dash y. So I am writing here ax plus v dy equal to a is this here, and dy dz is d dash y. So this is equation number 8. Now second point is converting d2y over dx to 2 times differential of y with respect to x in d2y over dz2. Now here we want to differentiate d2y over dx2. This converting in d2y over dz2. d2y over dz2. dx2 convert in dz2. So how we can change this? That will be possible in change of independent variable. So here d2y over dx2 in d2y dz2. So now then d2y over dx2. Here d2y over dx2, we can write this d over dx of dy over dx. Okay? D over dx, differentiation with respect to x of dy over dx. That is 2 times differential of y with respect to x, d2y over dx2. So here d2y over dx2, we can write this d over dx in bracket dy over dx. This equation 9. Here putting value of dy over dx from equation 6. What is 6 equation? 6 equation is this. This is 6 equation. So this 6 with the equation 6, we putting value here. From equation 6, putting value of dy dx in equation 9, then we get 9 is this equation. Then we get here d2y over dx2, d over dx, differential with respect to x here. Now here dy dz, and this is the value of dy dx. dy dx is equal to a upon ax plus v into dy dz. This is the value of dy dx. So dy dx putting this value putting here. Okay, this is equation 10. So here dy dx of a upon ax plus v into dy dz. So here are two function of x here, a upon ax plus v and dy over dz, and differentiating with respect to x. So we apply here product formula in 10. In equation 10, we apply product formula for differentiating of two functions, and both functions are in multiply. So differentiating equation 10 with respect to x using product formula. Product formula, what is formula? Differential of u into v. U is the function of x and v is also function of x. So we differentiate with of u into v. This is product formula here. U constant, differential of v, plus v constant, differential of u. Then we get the following result. So here d2y dx2, here a is constant, a taking out here. A is constant taking out. So we apply product formula. First of all here d over dx of dy dz into 1 upon ax plus v. dy this into this, here this into this. So a is constant, differentiation of this, differentiation of a up 1 upon ax plus v. So differentiation of d over dx of 1 upon ax plus v. So what is answer of this? Minus 1 upon ax plus v ka whole square. Ax plus b ka whole square and into a. This is the differentiation of 1 upon ax plus b. Okay. So we write this formula here. Minus a upon ax plus b ka whole square. What dy dz is constant. Plus dy dx of dy dz. Differentiating of dy dz with respect to dy dx. And 1 upon ax plus v is constant. So now we apply above formula. Formula is this here. Dy dx of 1 upon ax plus b dy dz. Differentiation of this constant. Plus differentiation of this. This is not here. D over dx of dy dz and this constant. So now here d2y dx2 equal to a minus a upon ax plus v ka whole square into dy dz plus d over dx of dy dz. Now here multiply dz and divide by dz. In this function we multiply dz and divide by dz into 1 upon ax plus b. Now this dz and this dx, this interchange to this. This is interchange to this. This dz writing here, dx writing here. Changing the place of dx and dz. In place of dx writing dz, in place of dz writing dx. So here differential with respect to z we get here. Because inside the function of z, dy over dz. So we can differentiate with respect to z this function. So but now out is d differential with respect to x. Inside differentiation with respect to z. So here we want to write differential with respect to that d over dz. So this process we can apply here. That is known as a change of variable here. So here a minus a upon ax plus b ka whole square dy dz plus d over dx dz, d over dz dy over dz and dz over dx. 1 upon ax plus b. Again from equation 6, putting dz over dx, value of dz over dx here. So we get here dz over dx is this equation 4. This value putting in equation 11. Okay, in 11 putting dz over dx a upon ax plus b. Value of from 4 putting in 11, then we get d2y over dx equal to a minus a upon ax plus b ka whole square into dy dz plus d2y dz2. This is the value of dz over dx putting in last equation a upon ax plus b into 1 upon ax plus b. This equation 13. A is common here. So we get here a square minus 1 upon ax plus b ka whole square dy dz plus d2y dz2. This into this. So this ax plus b ka whole square. So I am writing here ax plus b ka whole square. A square is common here. And this result. Now here ax plus b ka whole square taking this side. Yeah, multiply by ax plus b ka whole square in each term. Then this term is cancel out here. This term is cancel out. And this goes to this side here. So we get here ax plus b ka whole square d2y over dx2 equal to a square. Now here this dy dx, this is common. This result is common. Here d2y dz2 minus dy dz. So I am writing here minus dy dz plus d2y dz2. This equation 14. This plus, this minus. So positive term writing first here. d2y dz2. This writing there and this writing there. So d2y dz2 minus dy dz. This equation is 15. What we know here that dy dx is dy. d2y dx2 is d square y. And d cube by dx cube is d cube by. So here dy dx is dy and d2y dx2 is d square y and d cube by over dx cube is d cube by. This is all in all variable is x here. In these term variable is x, but in our question is variable z. Similarly dy dz here. Similarly dy dz is d dash y. dy is 2 d double dash square y. d cube by over dz cube d dash cube by. This equation 17. So now here from equation 15, 16 and 17 we have the following results. So ax plus b ka whole square d2y dx2 equal to a square d2y over dz2 minus dy over dz. This equation 15. So now writing derivative form here dy over dz. This is d dash y. d2y over dz2. This is d dash square y. And d cube by over d z cube. This equal to d dash cube and into y. In all variable here is z variable here. But in last result in our variable is x variable here. So here is writing d square d cube. But in here writing d dash cube, d dash y, d dash square, d dash cube. Here is dash. So writing this value here. This is d2y dx2 d square y. Ax plus b ka whole square into d square y equal to a square. This is d dash square minus 1 minus d dash. So d dash is common. D dash minus y. This equation 18. Similarly, we can prove the formula. Ax plus b ka whole cube d cube by over dx cube a cube d cube by over dz cube minus 3 d2 by over dz square plus 2 dy dz. This equation number 19. I am writing this equation direct. But with the above formula, above method, we can prove this result easily. But here I am writing directly this formula. If you want to prove, you can prove easily this. So here ax plus b ka whole cube d cube by over dx cube equal to a cube. This is d cube by over dz cube. This is result this d cube and d2y over dz2. This is d dash square and dy over this, that's dz and y is common here. This equation 20. So after factorizing this result, d dash cube minus 3d dash square plus 2d dash. So d dash is common here. D dash square and minus 3d dash plus 2. D dash square and minus 3d dash and plus 2. After factorizing this, we get here d dash minus 2 and d dash minus 3. D dash minus 1. So this is the formula here, d dash minus 1, d dash minus 2. So ax plus b equal to e to the power z. This equation 2. First we consider this. Let here ax plus b equal to e to the power z. And we get here z equal to log ax plus b. This is next result. First result this is considering here. First result equation 2 we have considered in our question. Then we can find this z equal to log ax plus b. This is equation 4. And now we find next formula with the help of equation 2 and 4. We have proved equation 8. So what is formula 8? Ax plus b dy dx equal to a dy dz. So ax plus b dy dx is dy and dy dz is d dash y. This equation 8 clear. Ax plus b ka whole square d square y equal to we have proved a square d dash minus 1 y. This is equation 8. Similarly we can prove x cube. Here ax plus b ka whole cube. Here is ax plus b ka whole cube and into d cube by equal to d dash minus 1 and d dash minus 2 into y. This is equation 20. With the help of equation 2, equation 4, equation 8, equation 18 and equation 20, we can change equation 1, general equation of Legendre homogeneous differential equation, that is general equation that is 1. That equation with the help of equation 4, equation 2, equation 4, equation 8, equation 18 and 20. These formula we apply in equation 1. Then equation 1 change in linear differential equation with constant coefficient in variable x to z. Okay. So this is the process. With the help of this process we can change our given question in Legendre homogeneous differential equation to linear differential equation with constant coefficient. Okay. So now we want to solve here one problem based on this Legendre homogeneous differential equation. So here problem 1 based on Legendre homogeneous linear differential equation. So what is problem? Solve 1 plus x. This is linear equation. 1 plus x. This is ax plus b here. A is 1, x, b is 1. A and b both constant are 1. So we write here 1 plus x. 1 plus x ka whole square d2 by dx2 plus 1 plus x dy dx plus y equal to 4 cos log 1 plus x. This is given question in our question paper. And we want to solve this question with the help of method of Legendre homogeneous linear equation. So first of all, this question is Legendre homogeneous linear equation. How we can say that? Because this is proof the property of Legendre homogeneous equation. What is property? Here is linear equation. The power of linear equation is 2. Multiply with second order derivative. Here is linear equation 1 plus x. The power of this is 1. Multiply with first order derivative. Here is linear equation, power is 0. So multiply with 0 order derivative. Here is 1 order derivative, 1 power. Here is 2 power, 2 order derivative. Here is 0 power, 0 order derivative. So here the power of linear equation is equal to the order of derivative and multiply with derivative in each term. Then this is known as a Legendre homogeneous linear differential equation. So now we want to this question in linear differential equation with constant coefficient with the help of the method change of variable. So we have discussed in last method. Similarly, we can write here directly. Solution here. Here we see that question is given in y and x. In our question, there are only two variables. First is y dependent variable, x is independent variable. Y is dependent on x here in our question. But now we want to change this question in y and z. y is dependent variable and z is independent variable. So this process is known as a change of independent variable. So here 1 plus x ka whole square d2y dx2 plus 1 plus x dy dx plus y equal to 4 cos log 1 plus x. This is equation 1. This is given question paper in our, this is question given in our question paper. Okay. So we want to change 1 x to z, x to convert in z, x to z. So here with the help of this process, here d is d over dx, dy dx is dy, d2y dx2 is d square y. So this is equation 2. This is all derivative with respect to x here. Equation 1 with the help of equation 2. This equation 1 and this 2 can be written as direct. We can write direct, putting this value dy dx equal to d and dy over dx putting dy, d2y dx2 d square y. This value putting in our question 1, then we can write this 1 plus x ka whole square d square y, 1 plus x dy plus y equal to 4 cos log 1 plus x. This is equation 3. Let us consider that following assumption. Here we are considering some assumptions which are discussing in methods in detail. We have already just discussing this assumptions in our method. So ax plus v equal to e to the power z. This is equation 4. Here x convert, we want to convert x in z. So we considering this result. So then taking log on both sides in 4 we get log ax plus v. Ax plus v, same formula we apply here. Log e to the power z, apply formula log x to the power n log x. So here log ax plus v, z log e equal to log e is 1 here. So log ax plus v equal to z or z equal to log ax plus v. But in our question z equal to log 1 plus x here. Here z equal to log 1 plus x according to our question. So differentiating with respect to x here, we get here 1 upon 1 plus x. Where d is dy dx, d dash is dy dz. This equation 6. According above assumptions, we get the following result. 1 plus x dy dx is dy dz. This equation 7. 1 plus x dy dx is dy. dy dz is d dash y. This equation 8. 1 plus x ka whole square d2y dx2. This equal to d dash square y minus d dash y. This equation 9. 1 plus x ka whole square d square y. D dash is common here. So d dash minus 1 is y. This equation 10. Putting value from equation 2, 4, 8 and equation 10 in equation 3. From equation 2, from equation 4, from equation 8 and equation 10. Putting in equation 3. Then we get equation 11. Here d dash minus 1 y plus d dash y plus y equal to 4 cos z. Here log 1 plus x is z. So here putting this value. So here multiply d dash square minus d dash plus 1 y is common equal to 4 cos z. So d dash is cancel here. We get d dash square plus 1 equal to 4 cos z. This equation 12. This equation 12 convert in linear differential equation with constant coefficient in variable z. This is linear differential equation with constant coefficient z of second order. Now we can solve with the help of CF plus PI. We apply here formula y equal to CF plus PI. So here d dash square y equal to 4 cos z. This equation 13. Here q is not 0. Condition is here q is not 0 here. Q is here 4 cos z. So here this equation right is f d dash y is equal to q. This is the type of equation. This equation in the type of this, where f d dash equal to d dash square plus 1 and q is 4 cos z. Equation 13 is known as a constant coefficient. This equation 11 is in y and z. This equation 13 is y and z, not 11. This is 13. 13 is y and z. And in our question is y and x. So this is change in independent variable. Solution of equation 13 is in two parts. First part is complementary function. Second part is particular integral. Now finding CF of equation 13, then putting RHS of 13 equal to 0. What is RHS? RHS is Q. Q is cos Z. Cos Z is equal to taking 0. Then we get here d dash square plus 1y equal to 0. This is equation 14. Now change equation 14 in an auxiliary form. Then putting d equal to m, d dash equal to m, d dash equal to m, and removing y from 14. Then we get an auxiliary form. We get an auxiliary form. Auxiliary form. We get an auxiliary form. So m square plus 1 equal to 0. This equation 15. Factorizing 15, m square equal to minus 1. But we know that I square equal to minus 1. Minus 1 is I square. So m square equal to I square. So after factorizing, m equal to plus minus I. M equal to plus and minus I means m equal to 0 plus minus I. This equation 16. M equal to alpha plus minus I beta. These are real imaginary roots. Roots are imaginary. Roots are imaginary. Imaginary roots. So roots are m equal to alpha plus minus I beta, where alpha is 0 after comparing. Alpha is 0 and beta is 1. Formula for CF of 1 if roots are imaginary. We have discussed this formula several times. If roots of an auxiliary form are imaginary, then we can apply this formula. So complementary function e to the power alpha x, c1 cos beta x, c2 sin beta x. This is formula 17. Putting alpha here 0 and beta is 1. Then we get CF. CF is e to the power 0x, c1 cos z plus c2 sin z. CF is c1, this is 1. c1 cos z plus c2 sin z. This is 18. Equation 18, this is complete complementary function of equation 13 in z. We get this is the complementary function, complete complementary function of equation 13 in z. So now solution of equation 13 is pi. Second. Now second solution of equation 13 is pi. So pi is equal to be apply this formula, particular integral 1 upon f d dash q. This is 21 equation. Putting value of here f d dash and q. Both value putting in 21. So putting value of f d dash and q in 21. So pi equal to 1 upon d dash square plus 1. Q is cos z, 4 cos z. This is equation 21. So here cos ax is cos x. So a is here 1. Apply case 1, putting d dash square equal to minus 1 square in 21. But we see that f minus a square, a function d square putting minus a square. Minus a square means minus 1 square. Minus 1 square means minus 1. So this is 0. In our question 0. Then pi is not complete. Then apply case second. So here 1 upon d square plus 1. So d dash square here. This equal to minus 1 square equal to minus 1. Writing this. So this result is 0. Denominator is. So this is 0 here. Then f minus 1 square. This result is 0. After putting this result, we get 0. Here apply case second. What is case second? In case second, we apply this formula. 1 upon d dash square plus a square cos az. Here putting d dash square equal to minus a square. Then this result 0. Then we apply direct formula. Z upon 2a sin a z. We have discussed this standard formula in last lectures. How we can find pi of this function directly. One function this, other function this. We have discussed these two formula direct. So what is value of this? 1 upon d dash square plus a square cos az equal to z upon 2a sin az. This formula we apply in our question. So now if there is d dash square plus a square sin az, then answer is in minus z upon 2a sin az. Sin here cos az. This is not sin az. This is cos az. Okay. So now pi equal to 1 upon d dash square plus 1 4 cos z. This is 21. Here apply d dash square equal to direct formula apply, not putting value. So 4 is this number and z upon 2a. A is 1 here. A is here 1. Z upon 2a sin z. This is complete pi of equation 13 in z variable. So now complete solution of equation 13, y is equal to cf plus pi in variable z. This is very important. You know, if you writing answer, then your answer should be in x or in z. There are two variables. So first you find the answer in z. After putting the value of z, then you get the answer in x. If you get the answer in x, then you find the complete solution of equation 1. If you have answer in z, then you write the solution of given question, changing equation. So here y equal to c1 cos z plus c2 sin z, cf in z means this is the cf of 13 and pi. This 2 cancel 2z. So 2z sin z, 2z sin z. This is 26 equation in z answer. Z answer means this is complete solution. This is complete solution of 13 equation. Okay. Now putting value of z here. Now putting value of z equal to log 1 plus x. In 26 then we get solution of equation 1. So y equal to c1 cos log 1 plus x plus c2 sin log 1 plus x plus 2. This is the value of z, 2z. 2 log 1 plus x and sin, this is sin z, sin log 1 plus x. This is equation 27. So equation 27 is complete solution of 1 because this is answer in x, in independent variable x. Okay. So in today I have discussed the topic Legendre homogeneous linear differential equation. In our differential equation there are two variables y and x. But now how we can solve this equation? So we change this Legendre homogeneous differential equation in linear differential equation with constant coefficient. So we be considering some assumptions here. After considering some assumptions, we can change our equation in z form. So after converting in z form, x convert in z form, then our differential equation is known as a linear differential equation with constant coefficient. Then we solve the question after changing in y is equal to cf plus pi. Okay. Then putting the value of z in our first solution, then we get the solution of given question 1. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.